Section 1. The door that only opens one way, everyone has a moment they want to revisit. A sentence you wish you hadn't said, a risk you wish you had taken, a version of yourself that felt closer to who you meant to be. The desire to go back is almost universal, not just to remember, but to return, to stand again at a crossroads armed with hindsight. To relive. It feels imaginable. After all, we can rewind a video, replay a song, scroll upward through old messages. Our technology moves backward effortlessly. So why shouldn't reality? Because reality is not a recording. It is a process. And that process has a direction. Look around you. Ice melts, smoke spreads, people age. Memories accumulate. In every case, something moves from order toward disorder, from structure toward diffusion. You never see the opposite. Melted ice does not spontaneously reassemble into a perfect cube on the counter. Smoke does not gather itself back into a cigarette. Wrinkles do not smooth themselves overnight. These aren't just habits of the world. They are signatures of a deeper rule. Physics calls this the arrow of time, the observable fact that events unfold in one direction, forward, always forward. But here's what makes this strange. The fundamental equations governing particles, the ones describing motion, forces, and interactions, mostly don't care about direction. If you filmed two particles colliding and played the footage backward, the motion would still obey the same equations. At the microscopic level, forward and backward are both allowed. So why does your life move only one way? Why can you remember the past but not the future? Why does cause precede effect? Why does regret exist at all? The answer is not hidden in emotion, it's hidden in statistics. There is something about the way the universe is arranged that overwhelmingly favors forward evolution over backward reconstruction. Not because backward is impossible in principle, but because it is so unimaginably improbable that it might as well be. It's buried under odds so extreme they crush the possibility of return. And once you understand why, nostalgia begins to look less like longing and more like a violation of arithmetic. Section 2. The law that points forward, the reason time moves forward, has a name. It is called the Second Law of Thermodynamics. At its heart is a single idea. Entropy tends to increase. Entropy is often described as disorder, but that word can be misleading. A better way to understand it is this: entropy measures how many different microscopic arrangements correspond to the same visible state. Imagine a brand new deck of cards, perfectly ordered by suit and number. There is essentially one arrangement that looks exactly like that. There are astronomically many arrangements that look random. If you toss the deck into the air and let the cards scatter, the overwhelming majority of possible configurations will look disordered. Order is rare, disorder is abundant. The second law says that systems naturally evolve towards states that can be realized in more ways, states with higher entropy. This is not about preference. It is not about intention. It is about probability. Consider a hot cup of tea placed in a cool room. Heat flows outward until the temperature equalizes. Why doesn't the surrounding air spontaneously transfer energy back into the tea, making it hotter again? Because there are vastly more microscopic ways for energy to be spread evenly than for it to be concentrated. Even if the laws of motion allow both possibilities, statistics do not treat them equally. Forward evolution, from concentrated to spread out, is overwhelmingly likely. Backward evolution, from spread out to concentrated, is so unlikely that it effectively never occurs. And this statistical imbalance creates direction. When you watch cream mix into coffee, you are witnessing entropy increase. The swirling patterns dissolve into uniformity. The molecules move from fewer possible configurations to vastly more. To reverse that process perfectly, to unmix the cream, every molecule would need to retrace its path with exact precision. One deviation and the reversal fails. The odds of that happening spontaneously are not merely small, they are catastrophically small. And here is the crucial insight: the arrow of time is not written into the equations of motion. It emerges from probability. Time moves forward because forward corresponds to states that can exist in more ways. Backward is not forbidden. It is simply drowned by numbers. Section 3, memory only works one way if entropy explains why physical systems evolve forward. It also explains something more personal, why you can remember yesterday but not tomorrow. Memory is not magic. It is a physical process. When you form a memory, neurons in your brain change their connections. Synapses strengthen or weaken. Electrical activity leaves behind structural traces. Information is encoded in matter. That encoding requires energy. It generates heat. It increases entropy in the surrounding environment. In other words, remembering something is not a neutral act. It is a thermodynamic event. To remember the past, your brain must move from one physical state to another, a state correlated with an earlier configuration of the world. That process increases entropy overall, even if the brain itself becomes more structured internally. But what would it mean to remember the future? For that to happen, your brain would need to encode information about a state of the universe that has not yet occurred. More precisely, it would need to correlate itself with future conditions before those conditions physically unfold. That would require entropy to decrease. It would require the environment to spontaneously organize itself in such a way that information about the future becomes available in advance. Statistically, this is indistinguishable from a shattered glass leaping back onto a table. Memory points backward because entropy points forward. You remember the past because the past left physical traces, footprints in sand, photons reflected into your eyes, neural patterns shaped by previous events. Those traces are records created as entropy increased. The future leaves no traces. It has not yet scattered its information into the present. This asymmetry between past and future is not psychological. It is structural. The universe contains records of lower entropy states because those states existed earlier in its evolution. As entropy increases, information about previous order gets dispersed but not erased instantly. The past lingers as correlation. A future does not linger. So when you feel the flow of time, when you experience it as a current carrying you forward, what you are actually feeling is the direction in which records accumulate. You move towards states with more possible arrangements. You remember in the direction of lower entropy, and you are blind in the direction of higher entropy, not because of limitation, but because of mathematics. Section 4, the universe started with the impossible if entropy always increases. Then one question becomes unavoidable. Why was it ever low? A second law of thermodynamics does not explain the beginning. It only describes evolution forward from an initial condition. It tells us that disorder grows, but not why the universe began in such an extraordinarily ordered state, because it did. When we look back toward the early universe using the framework of the Big Bang, we do not see chaos. We see something shockingly smooth. Matter was distributed with astonishing uniformity. Temperature variations were tiny, 1 part in 100,000. On large scales, the cosmos was nearly perfectly even. That sounds disordered, but gravitationally, it was the opposite. Gravity changes the entropy story. For most systems, gas in a box, ice melting, and water, uniform distribution means high entropy. But for systems dominated by gravity, uniformity is extremely low entropy. Matter wants to clump. It wants to collapse into stars, galaxies, black holes. The early universe had not yet done that. It was balanced on a knife's edge. As cosmologist Roger Penrose famously calculated, the probability of the universe beginning in such a low entropy gravitational state is staggeringly small, on the order of 1 in 10 circumflex 10 circumflex 123. A number so large it defies visualization, not billions, not trillions, but a 1 followed by 10 circumflex 123 zeros. That initial condition is the real mystery, because without it, there would be no arrow of time. Entropy increases only because it started low. The past appears ordered because the universe began in a state of extraordinary order. A future appears open because disorder has room to grow. Time flows because the beginning was special. If the universe had begun in maximum entropy, fully clumped, fully collapsed, gravitationally exhausted, nothing interesting would happen. No stars, no chemistry, no structure, no observers asking questions. The arrow of time is not built into the equations of motion. The fundamental laws of physics from Newton to quantum mechanics mostly work the same forward and backward. They are time symmetric. What breaks the symmetry is the boundary condition. The beginning, the universe did not start typical. It started improbable. And every second since has been the unfolding of that improbability. Time is not a universal river. It is the consequence of a very specific, very unlikely starting point. And we are living inside its aftermath. Section 5, you can't go back by now. The pattern is clear. Entropy increases. Memory points backward. The early universe began in an extraordinarily low entropy state. Put these together, and something profound follows. You cannot go back. not because engineers haven't built the right machine, not because the equations are incomplete, but because reversing time would require reversing entropy. And entropy is statistical inevitability written into the structure of reality. To go back is not just to revisit a location, it is to restore the entire universe to a previous microstate, every particle in precisely the configuration it once occupied. The laws that govern those particles, from classical mechanics to quantum theory, are largely time-symmetric. In principle, if you reversed every velocity and phase exactly, the equations would run backward, but that word exactly destroys the fantasy. A macroscopic system contains on the order of 10^30 particles. A human body contains vastly more. The observable universe contains around 10^30 to reverse time. You would need to reverse every degree of freedom with infinite precision. Any microscopic deviation, even one particle off by a quantum fluctuation, would cause the system to diverge almost instantly. Chaos would amplify the error, and entropy would resume increasing. This is not a technological barrier. It is a statistical wall. The number of possible disordered states vastly outweighs the number of ordered ones. The universe does not forbid backward evolution. It simply makes it so incomprehensibly unlikely that for all practical purposes, it never occurs. And even deeper, a time traveler returning to the past would carry entropy with them. Their body, their machine, their very memory would represent additional disorder injected into an earlier state. The act of arrival would prevent perfect restoration. The paradoxes people imagine, killing your grandfather, altering history, are not the real problem. The real problem is thermodynamic consistency. You cannot re-enter it without changing it. Time travel stories assume the past is a place. Physics says it is a condition defined by lower entropy than now. And conditions do not wait to be revisited. They evolve. The universe is not a film reel you can rewind. It is a statistical cascade from improbable order toward overwhelming possibility. You move forward not because you choose to. You move forward because the number of ways to be latter dwarfs the number of ways to be before. And that imbalance, silent, mathematical, relentless, is why you can't go back.